So far in our derivative rules, we've used the idea that we can take derivatives of sums or differences, products or quotients with our product and quotient rules of two or however many functions we want. But what would we want? What could we do if we had this problem where we had a composition of functions? Well, this is a job for what we call the chain rule. The chain rule essentially works like this. Let's say that we have two functions, and we'll call one y equals f of u, where u is just another variable, and u itself is a function g of x, and it's differentiable too. Well, if we take the composition y equals f of g of x, it's differentiable about x, and actually I'm going to go down here to this bottom part of the rule. It's differentiable, and we can see that if we were to take the derivative as x with respect to x of our composition f of g of x, it will be the derivative of the outer function f prime of g of x times the derivative of the inner function g prime of x. Now, we don't take the derivative of the inner part until we do that separately. Well, that seems a little strange. Another way of putting it, and this is using the Leibnitz notation right here for our dy dx, we say that if we are going to take the derivative of y with respect to x, then we are going to take the derivative of y with respect to u and multiply that result by the derivative of u with respect to x. We've actually done this, although we haven't really stated it this far. Let's say that I told you that we had a function like y is equal to x squared, right? This is a really basic function. Why would we even need a chain rule? Well, we've actually got two functions going on. In effect, we have the function y equals x going on, and we have the function, we could say, uh, let's see, y equals u squared going on, if we wanted to frame it that way, right? And so we're not really taking the derivative of y right here. We call this u right here, right? See what I'm talking about? U. So in this case, right, u is equal to x and y is equal to u squared. We know that if we take the derivative of y with respect to u, we're going to get 2u. And if we take the derivative of u with respect to x, it's a terrible looking u, my apologies to those u purists out there. The derivative of u with respect to x, well, we're going to get 1, right? So by this rule right here, dy dx, dy du times du dx is simply equal to 2u times 1, right? 2u times 1. But u was x, so when we rewrite this one more time, we're just left with 2x. It's sort of a long way around, but yeah, the derivative of y equals x squared is 2x, so there you go, right? It actually does work. Well, it seems like that's crazy. Why would we even do something like that? Well, that's the reason that we're going to use the chain rule here. Because what if we have a function that's not exactly the same way? Well, we can express it as what we call a general power rule. And this general power rule says this. Look, you're taking the derivative of some function x raised to a power n. So this rule says, well, all right, let's use the power rule. Only this time we're going to take n times that function f of x, and they raise that to the n minus 1 power, right? So we're not changing f of x. But then we're going to multiply it by the derivative of the inner function, okay? So in words, if a function is raised to a power n, then the derivative is n times the function raised to the power minus 1 times the derivative of the function itself. Another way of putting this is like we could say that if y is equal to some function u, where u itself is a function of x, then y prime, dy dx, is equal to n u to the n minus 1 times the derivative of u. So we've got that kind of situation going on right here. we have, in effect, the function y equals u cubed, where we're replacing u with the function 3x minus 5. So how would this rule work? Well, this rule tells me that if I want to find u prime, I'm going to take 3 times u squared, but then I want to multiply it by u prime. What's u prime? Well, u prime is the derivative of this inner function. U prime, in this case, this is a really simple one, is equal to 3, right? The derivative of 3 times 1 minus 0. So replacing u and u prime with their equivalents in terms of x, y prime is equal to 3 times the function 3x minus 5 quantity squared times 3. And simplifying that one more time, we might say y prime is equal to 9 times 3x minus 5 squared.